good afternoon, everyone. Great to be here in Bangalore. I was here just before COVID, and now I'm back. I see that COVID didn't do any bad to this beautiful institute. So that's great. And yes, so I'm going to talk about topics related to something that I've been doing a lot in the past years, which is called generalized hydrodynamics. And mostly the work, I will talk about this paper that is an archive, and the work is done with Leonardo Biagietti, which is my PhD student in Cergy, close to Paris, and my collaborator Benjamin Doyon, with his student Frederic Jupp. Okay, so the focus mostly is on one-dimensional many-body system, especially quantum many-body system, which is one of the biggest achievements on nowadays experimental settings. Really, experimentalists can trap atoms in quasi one-dimensional geometries and probe a lot of properties of them, different labs around the world. A lot of these systems actually, either if there are bosonic particles or fermionic particles, or in this case, like spin degrees of freedom, actually are described dynamically by quantum Hamiltonians that are integrable. If you don't know what it means, I will just tell you in a second. But the focus in the past years has been really on understanding the dynamics of this quite specific type of Hamiltonian that still have a lot of generical properties. So the simplest integrable model you can think of is really a model for kids, and it's just a model of one-dimensional hard spheres, also called hard rods model, or also Thom's gas. It's the model of particles in one dimension. So since it's one-dimensional, you can just see them as rods of size A, which scatter just elastically. So when they scatter, they just exchange their velocity. Okay, so now theta prime are the incoming velocity, and after they scatter, they have exchanged their velocity. So of course, this means that if you actually follow one single particle, its velocity is going to change in time. But you can just decide to follow the tracer, which is basically you follow the quasi-particle that keeps always the same velocity. So because velocity is just exchanged, the initial set of velocity at the theta is preserved in time. That's, in a sense, the definition of integrability. And so you can do nice figures like this, and you can see like trajectory of these particles. And if you follow the tracer, you see that basically it will undergo some kind of random motion, but with some well-defined velocity, that is the average velocity. This velocity is also called effective velocity because it is renormalized by the interaction with all the other particles in the system. And there is also a spreading around this velocity, which defines some kind of diffusion in the model. So there is a simple formula to compute this effective velocity given the densities of velocities in the system. This goes back to the work of Leibniz, of Herbert, and other in the 80s. And there really they managed to show that this is really a toy model, not only for integrability, but really for hydrodynamics. Because you can basically divide your system into big fluid cells, and in each fluid cell you put many of these particles, and now you talk about the distribution of velocities of this particle at given position x and time. And the time evolution of this density follows some kind of Navier-Stokes equation. Namely, there is a gradient spreading given by the current of this velocity, which is just given by the current of this particle, which is just given by this effective velocity times the density, and some diffusive spreading around, indeed given by this random motion of this quasi-particle in the fluid. Now, this equation, which up to a few months ago was believed to be exact, even out of equilibrium, is really been established a long time ago. And really, history of science sometimes is very peculiar because you can have like trajectories that of scientists that stay away and they never meet, and then at some point there is a click and you join and you make new theories. And that's really what happened, because from one side, this hard rod theory, you can see that basically was at the beginning of what is called soliton gas theory In a sense, like all the theory that look at more complicated type of particles, like solitons in partial differential equations, that still undergo typical similar type of scattering. And instead, the community of that I come from more, that is more the quantum community, which is the one of integrable models. And in 2016, actually, this community, in a sense, rejoined, because really the key point was to understand that exactly like hard rods, there is a lot of other quantum Hamiltonians, also classical, that are characterized by a set of quasi-particles that have given momenta that exactly like the hard rods. And when they scatter, they do exactly like hard rods. They exchange, if you want, the set of momenta. There is a given scattering shift, which for hard rod is just the size of the rod, A. But for generic model, it can be a function of the velocities divided by another function of the momenta, but still is a well-defined function. And scattering is only two-body scattering. So that's another definition. Models that include this class are indeed Lieb-Liniger, nonlinear Schrödinger, Stein-Gordon, and any integrable spin chain, Fermi-Hubbard, and so on. And so they really opened like Pandora vase of opportunity, because we understood that this equation that was initially written in the 80s for hard rods actually is valid for a huge class of models because they all share the same renormalization of the velocity in terms of scattering shifts, and also the same type of diffusing spread. So now this equation had a lot of applications and a lot of studies. Remarkably, really I was going to flash this. Experimentally, it's been verified in different settings, like a group Isabelle Bouchoul in Paris, a group of David Weiss. You really can probe for example, in this case, you really can probe how initial density wave of atoms spread in space. And you can check with the prediction of this equation, and you can really, in this case, you can really show superiority of this equation compared to standard hydrodynamics, because standard hydrodynamics, in a sense, it would be just to reduce this equation to just the density and energy and momentum of this quasi-particle. Instead, here you really have to look at the whole distribution of momenta. Okay, standard hydrodynamic would fail, would develop shocks and so on, other problems. Instead, this equation can keep going on and really reproduce experimental data. So, okay, that was big success of the theory. Now, just quickly, how do you derive hydrodynamics? So we had to, in a sense, go back a bit to the basic to understand actually what we were doing. And really, hydrodynamics is really a theory for the density of conserved quantities, which means that if you have a total conserved quantity that you can always write as the sum of local densities, you have to be a bit careful, by the way. You have to choose now this operator in a wise way, because there is always a gauge. But that's okay. That's a story for interested people, if you want to ask me. Then you write a continuity equation for these quantities, and then you do what people call fluid cell approximation, which means that now you coarse grain your space, and you say, okay, in each of these fluid cells, I assume some kind of local relaxation, which means that I can say that there is some kind of density matrix. Now, this is for quantum, but you can do the same exactly for classical. That looks a bit like this. So there is some set of chemical potential that smoothly depend on space and time. And then, of course, you can do what people call hydrodynamic expansion. You expand each of these chemical potential around the given position in terms of their gradients. And if you do that, then you can finally manage to write, because the whole point is how to write the current, expectation value of the current, in terms of the expectation value of the charge. You have to close the equation. Then you do that and you write this function in terms of the charge and their derivative. And you arrive, for example, if you stop at the first two orders, at the so-called Navier-Stokes equation, right? Which is the equation where the dynamic of the charges is given in terms of current evaluated in each steady state, plus the effect of the slope, which is parameterized in terms of the Onsager equation, or if you want, this product is also called diffusion matrix. Okay, and this Onsager matrix is actually given by the Green-Kubo relation, is evaluated by time integrating current correlators. Now, of course, in general, people stop here because no one knows how to compute this object in an interacting theory. But in integrable system, actually, you can do it. You can do it, and this is a remarkable properties of integrable system. It has to do with the fact that basically there is a simple way to understand diffusion in these systems, and it has to do with hydrodynamic projection. Okay, hydrodynamic projection, it's exact in integrable system. So what does it mean? It means that you can take your current as operator or as functional in classical theory and really project it on first on charges and then on charge fluctuations. And you can keep going on as much as you want. And now you know the dynamics of these charges. Basically, the way you do is you map the charges to the normal modes of the hydrodynamics. Basically, you diagonalize this matrix, which is called convective matrix. So now the normal modes are the modes that really move with a given velocity. And if you do that, basically you arrive to a closed expression for this Onsager matrix, which is really the sum of the current projected on the fluctuations of normal modes. This is an idea that also has been called diffusion from convection, the way we initially did it with Marco Mergendiak. And really, it's the fact that basically in these models, you have ballistic modes that propagate, and when they interact, basically there are density fluctuation, and this density fluctuation is what exactly leads to diffusion spreading. This is exact in integrable model. Now, this type of diffusion is very different compared to standard diffusion. Now, standard diffusion typically means that you take your current and you add some thermal noise to it. So, for example, as you would do in MFT. So you have some diffusion constant and you add some thermal noise, and this thermal noise typically is delta correlated in space and time, some just thermal agitation. Because you're basically tracing away all the rest of your degrees of freedom, so you have some kind of memory-less kernel in your theory. Integrable model, indeed, is completely different type of diffusion. You have some initial fluctuation in your initial state, which then propagate ballistically. They propagate in a deterministic way. But still, they give rise to diffusion because when your current is a function of the charges, and these charges locally fluctuate. So in order to see diffusion, basically, you have to basically expand your current in terms of the conserved quantities and look, for example, at the quadratic fluctuation of these charges in terms of your current. And this is really a different paradigm compared to standard diffusion. And this, in a sense, the noise now cannot be delta in time. It has to be spatially and time correlated, because the noise is advected. Okay, so it's the initial noise that gets propagated, and this gives rise to a lot of anomalous behavior. It's still diffusion, but anomalous. A way to see it, I mean, maybe the most direct way to see it is really to look at full counting statistics. Okay, so and I show you the result of this paper where basically they really show that this is not true only for integrable model, but as long as you have one ballistic mode in your theory, you can have this type of anomalous diffusion that I'm pointing out. For example, you can take a quasi one-dimensional fluid or spheres. So this would be like a tube with some width. Okay, so that is not the hard rod. That's not integrable. But still you have one ballistic mode due to momentum conservation on this direction. Then if you look at the charge transport between the two sides, namely at the fluctuation of this charge transfer, basically you construct what is known as full counting statistic. This increase with power t to the 1/4, which you already have seen from this problem of single phi diffusion. But the full counting statistic is not Gaussian. Okay, it's not Gaussian, as would be for standard diffusion. It's some non-Gaussian function. Okay, and in this case, it's a bit more smoothed out by the fact that you have a finite width. It's still non-Gaussian, but it's closer to a Gaussian. Then instead, if you take a purely one-dimensional model with one ballistic mode, which is just TASEP, you take TASEP, which is model for particle jumping, but they can only jump in one direction.
and you put some charge on top of it. Okay, you can just basically, you take TASEP and you assign some random charge +1 or -1 to each of these particles, and again you look at the charge transfer between the left and the right. Of course, you have some ballistic front, but you can just subtract the ballistic front and just look at the fluctuation around this ballistic front. Fluctuation still goes with the power 1/4, again, single file diffusion, but the full country statistic is not Gaussian. It's really far from being Gaussian. It's this very peculiar function that actually you can write as the convolution of a Gaussian with it. And this function actually, it's really shown to emerge in different type of single file systems, but with ballistic transport. So basically we are considering like single file problems, but where the particle, instead of being Brownian, they're actually ballistic. Okay, so they keep more memory of the previous condition. Now, these are an example of how anomalous transport can get in this type of system. What we have pointed out is actually also the fact that the major assumption that we do when we do hydrodynamics, which is this fluid cell approximation, actually must fail. It must fail because if you think about it now, you have a bunch of particles that carry ballistic information in your system. So in a sense, there has to be some notion of long-range correlation when the system evolves. And this has been indeed our work to show it. Indeed, basically, you take like a 2-point correlation at the same time between charges, different charges, so a space x prime. Even if at equilibrium these are delta correlated, okay, at equilibrium it's in a thermal state or in a generalized thermal state, these are delta correlated with this matrix also called susceptibility. Its evolution actually is given by an equation where, again, you can write it using hydrodynamic projection. This A is this convective matrix which I showed you before. But now, because this A actually can be x-dependent, again, because basically the effective velocity in the system can fluctuate in x due to the density weight in your system. Now, this delta-like correlation is not preserved, okay? So it would be preserved if I would factorize this A outside, if this A would not depend on x and x prime. And that would be preserved, no problem. That's what happened in free system. If you take hard rods and you send the size of the rods to 0, then you will not have this effect. But because here, locally, velocity depends on space, the initial delta is not preserved, and these are very nice plots of what you get in hard rods for this 2-point correlation. Here is for density and momentum correlation at different point x and y. And you see that indeed after like some kind of a domain wall quench, where you let particle to rearrange, so you have this big wave at the beginning, this wave then redistribute, and then at large time you have this special correlation that are flat over the whole system, at least on a scale order of time. And of course, you see the signal is very small, so we had to run like billions of samples to see this, but it's fine. And of course, if this is true, then you cannot do any more Kubo-like, you cannot derive any more hydrodynamics as you used to do. So you have to again use a bit more refined technique, which is, for example, ballistic macroscopic fluctuation theory, which is nothing than more mathematical way of saying what I already just told you, which is basically the fact that in order to do hydrodynamics, you have to start from fluctuating initial state, then expand the current on top of this fluctuation, and then basically your correct hydrodynamics is something that looks like this, where diffusion is indeed regulated by the fluctuation of the current with respect to the charge, and this one is just basically the 2-point function of the charges. So in a sense, it's a bit like in BBJKY, where you map, in order to have the evolution of the 1-point function, you need the evolution of the 2-point function, which we can do, and so on. And we can show that if you are close to linear response, if your initial density waves are very small or short times, these recover completely normal Navier-Stokes diffusion. So you have, again, diffusion constant time slope of Q. But if you are far from linear response, or if you wait long time, you have the onset of long-range correlation. Navier-Stokes is not valid anymore. You really have to keep all these terms here. And here, okay, we have done some numerics to show the difference. So in a sense, the black curve is the exact simulation. The green one is what you would get if you use Navier-Stokes, and the red one is the one if you use this. You see, the differences in this setting are really small. It's more, in a sense, it's more a conceptual point. It's really the idea that it's wrong to use Navier-Stokes. Of course, it's just in this system where these long-range correlations are small. There are, of course, other systems where you can have much stronger correlation. And this brings me to the conclusion. So what I try to convince you is that even whenever you have ballistic modes, which is the case in integrable models, but also in non-integrable models, you can have ballistic modes due to symmetry, for example. Whenever you have a conservation of momentum in one direction, that gives you automatically one ballistic mode. Or in the case of TASEP, for example, diffusive fluctuation will probably be anomalous. So it means that you may see diffusion if you look at the spreading of charge, but if you actually probe better, you see that it's not exactly what people call normal diffusion. In particular, what is called Kubo diffusive hydrodynamics, the one that you derive using hydrodynamic fluid cell and expanding, it can be wrong. So you can deviate from the usual Navier-Stokes equation due to the presence of long-range correlation that can be in the system that develop in the system during hydrodynamic evolution. And this basically is opening the way to really to try to understand more about system with ballistic modes. So of course there is a work in progress on developing a much better ballistic fluctuation theory, and for example trying to understand what would be the equivalent of a stochastic formulation of generalized dynamic equation, since it clearly cannot be simply taking the current and adding some delta correlated noise, as I tried. And with this I'm done. Thank you for your attention.
Thank you.
Yeah, can you say something about whether you expect a finite number of hydrodynamic fields to describe these systems completely, or is it necessarily an infinite number? Is it only mass, energy, and momentum densities, or will there be many others?
No, so indeed, for generalized dynamic system, that's based on infinite number of modes.
Right.
So, for example, for the hard rods system, yes, you have all the distribution of momenta to keep. Mm-hmm. That's your hydrodynamics. But what I wanted to point out is that the mechanism that I'm showing of anomalous diffusive does not rely on the infinite number of modes.
Right.
It really relies on the existence of at least one ballistic mode and some coupling with the other modes.
So when you say ballistic, supposing I took an ordinary fluid, the total momentum is conserved. So to some degree, some part of it goes through ballistically. That itself, let us say for a low-dimensional fluid, gives you anomalous scalings like the 3 hours launch.
Well,
so this is like that on steroids, or what? I mean, how should we think about it?
No, okay, so you cannot see this anomalous behavior really. Imagine that now I take this width and I expand it, right? And I really look at the charge transfer between left and right.
Yeah.
Then I would have the sum of many anomalous independent process. So by universality of the central limit theorem, at the end I would get Gaussian. So in a sense, in order to see this anomalous behavior, I have to look at one thin slit, because that's really where I can probe the one-dimensional current. If I just probe many one-dimensional current, then I will just see normal diffusion. This anomaly will be removed.
Nice.
But what I'm saying about long-range correlation, that would be also true. If I take to this system, I still expect to see some kind of long-range correlation in the direction where the flow is going, yes.
Okay.
Now, how it affects then hydrodynamics depends a bit on...
Thank you very much. Always illuminating. I have one question. When you look at the hard rods, despite, of course they have the simplification that, it should have I mean, the scattering shift is always the same, but there's a second simplification that you can always exactly identify what the quasi-particles are. Now, when I look at other integrable systems, and let's say at high density, then you see there are a lot of regions where you don't even know where the quasi-particle is, but then maybe there are further on some regions, where you can actually identify it. I mean, does this somehow, for instance, at high density, is this picture still sort of correct, or does it have to be modified? I mean,
you mean if Navier-Stokes is
because
no, I don't expect to be correct in high or low density limit. Here, really, the distinction is between.
Well, I mean, it's just this picture of a quasi-particle moving and making jumps. I mean, is a very rough picture at high density. I mean, that's all what I'm saying.
Yes, but to me, this is really like a picture to show you, to tell you why there should be long-range correlation. Well, you can really prove that there is always long-range correlation as long as you are away from linear response. So it's not linear and low-density ions. It's really like how your non-equilibrium protocol is probing.
These ballistic fluctuations that give rise to anomalous diffusion, will it be also true if your initial state is homogeneous completely?
No, that's what I'm saying. Yes, that's what I'm saying. If you are, okay, depends what you ask. So if you ask if this equation, if Navier-Stokes equation is correct, yes. Close to equilibrium, it will be correct. Yes. But if you ask about full counting statistic, then even the full counting statistic at equilibrium, it will be strongly non-Gaussian. So this is actually, this plot here for the full counting statistic is for equilibrium fluctuations.
Possible to say that there is a coefficient like D, which is some second moment of some distribution, but for one particular realization of initial conditions, you can describe this generalized hydrodynamics in terms of a few numbers like D, second moment of something or the other, and this number may depend on the initial condition. I don't need an infinite number of constants, only 2 or 3, but those 2 or 3 may be some moments of some other stuff.
So you want to say that you want to, instead of writing an equation that look like this, which for many components, you want to write an equation with less modes, but like fluctuating, with fluctuating.
I will just say that this D you have is an initial condition dependent function number.
This D? Yes, that maybe, but I don't think that would save you from having many components. No.
Okay.
It's really like the fact that, so for example, in this setting was really done to show that you cannot resolve the dynamics here to finite components, because finite components would display eventually always a shock, while generalized dynamics is shockless theory.
It's like in your numerics, like difference looks small, but like how many particles were there? Like you said, you like huge number of realization. But what was the number of?
No, but the smallness here is not order 10,000 or even millions of. It's really like this. There is not 1/n effect here.
There's not a finite size.
No, because we have. I mean, we really had to run in order to see these differences. Because you see, I mean, the long-range correlations that you develop, at least in the setting we studied, are so small that the deviation, because your deviation are due really to this correlation, to this presence correlation, of course your deviation is expected to be small. That's a feature of hard rods, and I mean, it's because we know how to simulate hard rods, so we have a bit confined to this model, but you may imagine that there are models where you can get stronger deviations. Actually, I think that you will see really the place where to see the deviations stronger here is if you include an external trapping potential.
So the other question was like even in non-integrable systems, like you have bare transport coefficients, but then but when you do hydrodynamics, they get renormalized, and the transport coefficients change a lot, right? I mean, they can diverge and so on. I mean, is this sort of similar?
So you mean if you add noise, transport coefficient can be renormalized, right?
Right. Yeah.
It's a bit like what happened in Berger equation.
Burgers, or even like the FPU and so on.
Yeah, It's a bit similar in a sense, like this is telling you that you cannot neglect fluctuations. But fluctuation, the whole point is that in Berger, you would just add this noise additively. Here you cannot do it would not be correct. The correct way is to have initial fluctuation and propagate them. And if you do that, then yes, you get the correct equation, which is not Navier-Stokes, but is this one. That is exactly the point, yes.
Long live India and France friendship.